During the Cold War, fear was shaped not only by nuclear warheads, but by the scale of the systems built to deliver, detect, survive, and retaliate. The Soviet Union pursued mega-projects that pushed engineering, geography, and human endurance to their limits, often in secrecy and at continental scale. These were not symbolic undertakings or experimental curiosities. They were integrated instruments of power, designed to alter strategic balance and psychological perception. From colossal radar arrays and Arctic submarine fortresses to orbital stations and automated retaliation systems, each project signaled an intent to dominate escalation, endurance, and survivability. To Western intelligence agencies and military planners, these undertakings were terrifying, not because they were always perfect, but because they demonstrated a willingness to invest enormous resources into systems meant to function during the worst possible moment in human history. Duga radar system, the Soviet over-the-horizon signal that haunted NATO. The Duga radar system was one of the most secretive and intimidating technological projects undertaken by the Soviet Union during the Cold War. Designed to detect incoming intercontinental ballistic missiles at extreme distances, Duga represented an attempt to peer beyond the curvature of the Earth itself. Its existence signaled to Western intelligence agencies that the USSR was investing heavily in early warning systems capable of reshaping nuclear strategy. Development of the Duga system began in the late 1960s and continued through the early 1970s under Soviet military research institutes focused on strategic defense. The system was classified as an over-the-horizon radar, meaning it used high-frequency radio waves bounced off the ionosphere to detect missile launches thousands of kilometers away. Unlike conventional line-of-sight radar, Duga could theoretically provide several minutes of warning before incoming missiles reached Soviet airspace. The most famous Duga installation was constructed near Chernobyl in the Ukrainian Soviet Socialist Republic and became operational during 1976 to 1989. The structure itself was staggering in scale. The main antenna array stretched approximately 700 meters in length and stood over 150 meters tall, dominating the surrounding forest. A second major installation was built in the Russian Far East near Komsomolsk-on-Amur, reinforcing the system's strategic coverage. To NATO monitoring stations and civilian radio operators alike, Duga was instantly recognizable. It emitted a rapid, repetitive tapping noise across shortwave radio frequencies, earning the nickname the Russian woodpecker. The signal was so powerful that it interfered with global communications, aviation, maritime traffic, and military transmissions. Western analysts quickly realized that this was not a malfunction or accident, but a deliberate and sustained military broadcast. The scale of resources devoted to Duga was enormous. It required its own power infrastructure, command facilities, barracks, and maintenance units, effectively functioning as a self-contained military complex. Thousands of personnel were involved in its operation, and its secrecy was such that even nearby civilian populations were largely unaware of its true purpose. Despite its ambition, Duga faced serious technical challenges. False positives caused by solar activity, atmospheric disturbances, and ionospheric instability made reliable detection difficult. By the early 1980s, advances in satellite-based early warning systems began to outperform ground-based over-the-horizon radar, reducing Duga's strategic value. Following the Chernobyl nuclear disaster in 1986, the nearby Duga installation was permanently shut down. By 1989, the system was abandoned entirely. Its towering antennas remain standing today as rusting monuments to Cold War paranoia and technological overreach. The Duga radar system terrified NATO not because it worked perfectly, but because it demonstrated the Soviet willingness to build massive, experimental systems in pursuit of nuclear advantage. It embodied a doctrine where scale, secrecy, and psychological impact were weapons in their own right, reshaping how the West assessed Soviet strategic capabilities. Buran Space Shuttle, Moscow's silent answer to the American shuttle. The Buran Space Shuttle was one of the most ambitious and expensive technological projects ever undertaken by the Soviet Union, created as a direct response to the American Space Shuttle program. While outwardly similar in appearance, Buran was conceived with different priorities, reflecting Soviet concerns about military balance, strategic surprise, and the weaponization of space during the late Cold War. Development of the Buran program began in 1976 after Soviet military analysts concluded that the American space shuttle could be used not only for civilian missions but also for deploying or recovering weapons in orbit. Soviet leadership viewed this potential capability as a strategic threat. Rather than risk falling behind, the USSR authorized the creation of a fully reusable orbital spacecraft paired with an entirely new heavy-lift launch system. Unlike its American counterpart, Buran was designed to fly without a crew. The shuttle itself had no main engines. Instead, it relied on the Energia rocket, one of the most powerful launch vehicles ever built. This design allowed Buran to carry heavier payloads into orbit and provided greater flexibility for military or industrial missions. The shuttle measured approximately 36 meters in length and had a payload capacity comparable to, and in some cases exceeding, that of the U.S. Space Shuttle. The Buran shuttle completed its first and only spaceflight on November 15, 1988. Launched from the Baikonur Cosmodrome, it orbited the Earth twice and returned to land completely autonomously, touching down with remarkable precision despite strong crosswinds. This automated flight was a major technical achievement, demonstrating guidance, navigation, and control systems that were more advanced than those used by any crewed shuttle at the time. Behind the scenes, the program consumed enormous resources. Tens of thousands of engineers, scientists, and workers were involved across hundreds of factories and research institutes. Specialized infrastructure was built to support Buran, including massive assembly buildings, launch complexes, transport aircraft, and tracking networks. The scale of the effort rivaled the largest industrial projects in Soviet history. Despite its success, Buran never flew again. By the late 1980s to early 1990s, the Soviet economy was under severe strain, and military priorities were shifting. The collapse of the Soviet Union in 1991 effectively ended the program. Funding was withdrawn, missions were canceled, and the remaining orbiters were placed in storage. In 2002, the only space-flown Buran orbiter was destroyed when the roof of its hangar at Baikonur collapsed. With it went the most visible symbol of the program. The Buran space shuttle haunted Western planners not through repeated missions, but through what it represented. It proved that the Soviet Union could quietly match, and in some areas surpass, American space technology. Even with a single flight, Buran demonstrated that the USSR was capable of building a reusable orbital system designed as much for strategic leverage as for exploration. Energia, heavy-lift rocket, a super booster built for strategic space power. The Energia heavy-lift rocket was the most powerful space launch system ever developed by the Soviet Union, created to give Moscow unmatched strategic reach beyond Earth. Conceived during the late Cold War, Energia was not designed as a single-purpose launcher, but as a universal super booster capable of placing enormous military, scientific, and industrial payloads into orbit. Its existence signaled that the USSR intended to compete at the highest possible level of space power. Development of Energia began in 1976 in parallel with the Buran space shuttle program. Soviet planners understood that true dominance in space required more than a reusable orbiter. It demanded a launch vehicle powerful enough to deploy space stations, large reconnaissance platforms, and potential military systems in a single launch. Energia was engineered as a modular system centered around a massive core stage powered by four RD-0120 liquid hydrogen engines, flanked by four strap-on boosters using RD-170 engines burning kerosene and liquid oxygen. Standing over 58 meters tall, Energia was capable of lifting more than 100 metric tons into low Earth orbit in its full configuration. This placed it on par with, and in some payload profiles beyond, the American Saturn V. Unlike earlier super heavy rockets, Energia was designed for flexibility. It could launch the Buran shuttle, massive space station modules, or large payloads mounted directly on its core without an orbiter. allowing it to support missions that were never publicly disclosed. Energia flew only twice, but both launches demonstrated its technical maturity. The first launch on May 15, 1987, carried the Polyus payload, a massive experimental spacecraft, widely believed to be linked to space-based defense research. Although Polyus failed to reach orbit due to a guidance error, the rocket itself performed successfully. The second launch on November 15, 1988, carried Buran on its only spaceflight, completing a fully automated orbital mission and landing without a crew. The industrial effort behind Energia was immense. Entire factories were dedicated to producing engines, cryogenic fuel systems, avionics, and structural components. The RD-170 engine family became one of the most powerful liquid-fueled rocket engines ever built, and later influenced rocket designs well beyond the Soviet program. Launch infrastructure at Baikonur Cosmodrome was expanded and reinforced specifically to accommodate Energia's size and fueling requirements. Despite its success, Energia was overtaken by political and economic collapse. By the late 1980s to early 1990s, funding evaporated, missions were canceled, and the dissolution of the Soviet Union ended the program entirely. Completed rockets were placed into storage, and future variants were abandoned. Energia unsettled Western analysts because of what it made possible. It proved that the Soviet Union possessed the capability to deploy massive payloads into orbit on demand. As a super booster built for strategic space power, Energia represented a level of potential that few launch systems before or since have approached. Typhoon-class submarine, the largest nuclear submarine ever constructed. The Typhoon-class submarine was the most imposing and complex undersea weapon system ever built, representing the absolute peak of Soviet naval engineering during the Cold War. Designed to ensure the survivability of nuclear deterrence, the Typhoon was not simply a submarine, but a submerged strategic fortress built to operate beneath the Arctic ice for months at a time. Development of the Typhoon class began in the early 1970s under Project 941. Driven by Soviet concerns over the vulnerability of land-based missile systems and earlier ballistic missile submarines. Western anti-submarine warfare capabilities were improving rapidly, and Soviet planners sought a platform that could remain hidden in the most inaccessible regions of the world's oceans. The Arctic, with its permanent ice cover, offered the ideal sanctuary. Construction of the Typhoon-class submarines took place at the Sevmash shipyard during the late 1970s to mid-1980s. Each vessel measured approximately 175 meters in length and displaced over 48,000 tons when submerged, making it the largest submarine ever constructed. To achieve this scale, designers adopted a unique multi-hull configuration, consisting of two parallel pressure hulls with additional compartments arranged between them. This design increased survivability and allowed unprecedented internal volume. The Typhoon was powered by two nuclear reactors, giving it virtually unlimited range and endurance. It carried up to 20 R-39 intercontinental ballistic missiles, each equipped with multiple nuclear warheads capable of striking targets thousands of kilometers away. These missiles were specifically designed to be launched through thick Arctic ice, reinforcing the submarine's role as a hidden second strike platform. Crew comfort and sustainability were priorities rarely seen in military submarines. The Typhoon featured relatively spacious living quarters, a gymnasium, a sauna, and recreational areas, all intended to support crews during extended patrols lasting several months. This focus on habitability was not luxury, but necessity, as prolonged Arctic deployments demanded psychological as well as physical resilience. The sheer size of the Typhoon made it extremely difficult to track. Operating beneath ice floes and remote polar regions, it exploited environments where Western sonar networks were less effective. NATO naval planners viewed the Typhoon as a major escalation in undersea warfare, forcing costly investments in new detection systems, patrol aircraft, and submarine hunting technologies. Despite its strengths, the Typhoon class was expensive to operate and maintain. By the late 1990s to early 2000s, arms reduction agreements and economic constraints led to the gradual retirement of most vessels. Only one was retained for testing and research purposes. The Typhoon-class submarine represented deterrence through overwhelming scale and survivability. By combining massive size, advanced missile capability, and Arctic stealth, it embodied the Soviet strategy of ensuring that no first strike could ever neutralize its nuclear forces, fundamentally reshaping how undersea strategic warfare was perceived by the West. Dead hand system, perimeter, and automated nuclear retaliation mechanism. The dead hand system, officially known as perimeter, was one of the most unsettling strategic projects ever conceived by the Soviet Union. Unlike missiles, submarines, or bombers, perimeter was not a weapon designed to be launched by human command in the heat of battle. It was a system built to ensure that nuclear retaliation would occur, even if the Soviet leadership had been completely destroyed. Development of the perimeter system began in the early 1970s, driven by deep Soviet fears of a decapitating first strike by the United States. Advances in precision weapons, submarine-launched missiles, and early warning technology raised the possibility that Soviet command structures could be eliminated before a retaliatory order could be issued. Perimeter was designed to remove that vulnerability entirely. The system became operational during the early 1980s. At its core, perimeter was an automated command and control network linked to sensors, communication nodes, and specially modified command missiles. These sensors monitored seismic activity, radiation levels, atmospheric pressure changes, and communication traffic. The system was not permanently active. It required human authorization during periods of extreme crisis, ensuring that it could not trigger accidentally during peacetime. If activated, and if perimeter detected signs consistent with a massive nuclear attack, combined with the loss of communication with Soviet leadership, it would initiate its final function. Instead of launching nuclear warheads directly, perimeter would fire command missiles into the atmosphere. These missiles broadcast encrypted launch orders to surviving nuclear forces across the Soviet Union, including missile silos, mobile launchers, submarines, and bomber bases. In effect, the system replaced destroyed leadership with an automated signal that guaranteed retaliation. What made perimeter especially terrifying to Western planners was its logic. It removed uncertainty. A successful first strike no longer meant neutralizing Soviet nuclear forces. It meant ensuring global annihilation. The system transformed nuclear deterrence from a question of decision-making into one of inevitability. The existence of perimeter forced NATO strategists to reassess every aspect of nuclear planning. Concepts based on disabling command structures or delaying retaliation lost relevance. Even partial information about the system amplified its psychological impact, as no external power could be certain when or how it might activate. Despite its fearsome reputation, perimeter was designed with multiple safeguards. Human operators retained control over activation, and the system required confirmation from several independent inputs before functioning. It was intended as a last resort mechanism, not a substitute for leadership. Perimeter remains one of the clearest examples of Cold War logic taken to its extreme conclusion. It embodied a worldview in which survival depended not on winning a nuclear war, but on ensuring that no adversary would ever dare to start one. As an automated nuclear retaliation mechanism, Dead Hand turned deterrence itself into a machine, silent, hidden, and designed to function when no one was left to give the order. Baikonur Cosmodrome, the world's largest space launch complex. Baikonur Cosmodrome was the physical heart of the Soviet space program and one of the most strategically important installations of the Cold War. Built in secrecy in the vast steppe of Kazakhstan, Baikonur was not just a launch site, but an enormous military-industrial ecosystem designed to project Soviet power far beyond Earth. Its sheer scale, isolation, and output made it a source of constant concern for Western intelligence agencies. Construction of Baikonur began in 1955 under extreme secrecy, officially disguised as an agricultural project. The site was chosen for its remoteness, flat terrain, and favorable latitude for orbital launches. From the beginning, Baikonur was intended to support both civilian space exploration and military missile development. It became the primary testing ground for intercontinental ballistic missiles before evolving into the launch center for satellites, crewed spacecraft, and heavy rockets. The size of Baikonur was unprecedented. The complex eventually covered more than 6,700 square kilometers, making it larger than many cities and military bases combined. It contained multiple launch pads, assembly buildings, fuel plants, tracking stations, rail networks, power infrastructure, and entire residential cities to house tens of thousands of workers, engineers, soldiers, and their families. Western analysts often described Baikonur as a state within a state. Baikonur was responsible for many of the most alarming milestones of the space race. From its launch pads came Sputnik, the world's first artificial satellite, Yuri Gagarin's historic first human spaceflight, early military reconnaissance satellites, and later the heavy launch vehicles that supported Soviet strategic ambitions. Each successful launch signaled that the USSR possessed not only advanced rocket technology, but also the industrial capacity to sustain it at scale. The Cosmodrome reached its peak importance during the 1970s to 1980s, when it supported massive programs such as Salyut, Mir, Energia, and Buran. Launch pads were built specifically to handle rockets of extreme size, including super heavy boosters capable of placing enormous payloads into orbit. The infrastructure required to fuel, assemble, and launch these vehicles reinforced Western fears that the Soviet Union was preparing for large-scale military operations in space. Baikonur's secrecy amplified its psychological impact. Western intelligence had limited visibility into its full capabilities, launch schedules, and payload purposes. This uncertainty forced NATO planners to assume worst-case scenarios regarding Soviet space-based weapons, surveillance systems, and rapid launch capacity. Even after the collapse of the Soviet Union, Baikonur remained operational, underscoring the durability of the project. Its continued use by Russia highlights how deeply embedded it was in Soviet strategic planning. Baikonur Cosmodrome was terrifying not because it launched rockets, but because it proved the Soviet Union could sustain space operations on an industrial scale. As the world's largest space launch complex, it embodied the fusion of military power, technological ambition, and secrecy that defined Cold War competition beyond Earth. MAZ-7907 Strategic Transport Program, Ground Mobility for Nuclear Giants. The MAZ-7907 Strategic Transport Program was one of the most extreme and secretive ground mobility initiatives undertaken by the Soviet Union, created to support weapons so large that conventional transport infrastructure was effectively useless. The program centered on a single purpose: ensuring that the heaviest strategic nuclear systems could move independently across vast distances away from fixed bases, roads, and predictable launch locations. Development of the MAZ-7907 began in the early 1980s at the Minsk automobile plant, during a period when Soviet strategic doctrine placed enormous emphasis on survivability through mobility. Western advances in satellite surveillance and precision strike capability had made static missile silos increasingly vulnerable. In response, Soviet planners sought ground platforms capable of dispersing massive payloads across undeveloped terrain, complicating detection and targeting. The MAZ-7907 was unlike any wheeled vehicle built before it. It featured a 12-axle configuration with 24 wheels, all driven through an electric transmission system. Instead of a conventional drivetrain, a gas turbine engine generated electricity that powered individual wheel motors. This design allowed precise torque control across the vehicle's enormous footprint and enabled movement under loads exceeding 150 to 200 metric tons under controlled conditions. At nearly 30 meters long and more than 4 meters wide, the MAZ-7907 was not intended to operate on public roads. It was engineered for unprepared ground, hardened soil, compacted snow, and ice roads in remote regions of the Soviet Union. Cold weather operation was a central requirement. and the vehicle incorporated extensive insulation, heating systems, and reinforced components to function in sub-zero environments, including Arctic and subarctic zones. The strategic value of the program lay not in speed, but in unpredictability. A vehicle of this scale could transport oversized missile components, experimental launch systems, or other classified payloads to locations far beyond established infrastructure. This forced Western intelligence planners to account for launch platforms that were not tied to known bases, rail lines, or fixed corridors. Testing during the mid to late 1980s confirmed that the MAZ-7907 could move its intended loads, but also revealed severe limitations. Fuel consumption was enormous, maneuverability was extremely limited, and maintenance demands were extraordinary. Operating the vehicle required specialized crews, support vehicles, and carefully planned routes, making routine deployment impractical. As the Soviet Union entered economic crisis in the late 1980s to early 1990s, the program lost momentum. Strategic priorities shifted, funding declined, and the collapse of the USSR effectively ended further development. The MAZ-7907 never entered full operational service, remaining an experimental platform rather than a deployed system. The MAZ-7907 Strategic Transport Program unsettled Western analysts because it represented intent rather than execution. It demonstrated that the Soviet Union was willing to build ground vehicles at unprecedented scale to preserve nuclear mobility. As a concept, it expanded the battlefield itself, turning vast stretches of land into potential launch zones for nuclear giants and reinforcing the logic of deterrence through dispersion and uncertainty. Project 941. Naval Infrastructure. Arctic bases built for submarine warfare. Project 941. Naval infrastructure was the hidden foundation that made the Typhoon-class submarine program possible. While the massive submarines themselves drew attention, it was the vast and largely unseen network of Arctic bases, ports, and support facilities that truly alarmed Western intelligence agencies. These installations transformed the frozen northern coastline into a fortified sanctuary for strategic nuclear forces. Development of Project 941 infrastructure began in the early 1970s, alongside the design of the Typhoon-class submarines. Soviet naval planners recognized that vessels of such unprecedented size and displacement could not operate from existing bases. New facilities were required, specifically tailored to Arctic conditions and designed to support prolonged under-ice operations. The result was a massive construction effort focused on the Kola Peninsula and other high-latitude regions. Key bases such as Zapadnaya Litsa, Nerpichia Bay, and Severomorsk were expanded or built almost entirely from scratch. These installations included reinforced submarine pens, deep-water piers, missile handling facilities, nuclear reactor service areas, and specialized dry docks capable of accommodating submarines displacing over 48,000 tons. Many structures were hardened against attack, with underground tunnels and blast-resistant storage areas carved directly into rock. One of the most critical aspects of Project 941 infrastructure was its ability to support under-ice operations. The bases were positioned to give Typhoon-class submarines rapid access to Arctic ice fields, where thick ice cover provided natural concealment. Specialized icebreaker support, navigation systems, and communication networks were integrated to allow submarines to deploy, patrol, and return without surfacing in open waters. Logistics were equally extensive. Entire towns were built to house tens of thousands of sailors, engineers, technicians, and their families. Power plants, rail connections, fuel depots, and command centers formed a self-sustaining military ecosystem operating year-round in extreme cold. The scale of investment rivaled that of major industrial cities, all dedicated to a single strategic mission. For NATO planners, Project 941 infrastructure posed a profound challenge. These Arctic bases allowed ballistic missile submarines to remain hidden beneath ice for extended periods, severely limiting the effectiveness of Western anti-submarine warfare systems. Traditional tracking methods were far less effective in ice-covered waters, forcing costly development of new sonar technologies, patrol routes, and surveillance strategies. The infrastructure also complicated any potential preemptive strike scenario. The dispersal of submarines, combined with hardened and concealed base facilities, meant that eliminating Soviet sea-based nuclear forces would be extraordinarily difficult. Even partial survival ensured devastating retaliation. Although many Project 941 facilities were scaled back or decommissioned after the late 1990s to early 2000s, their impact endured. They reshaped naval strategy in the Arctic and demonstrated how geography, engineering, and scale could be combined to protect strategic weapons. Project 941. Naval infrastructure terrified the West not through visibility, but through permanence. It turned the Arctic into a fortified nuclear bastion, ensuring that Soviet submarine warfare capabilities remained hidden, protected, and ready beneath the ice. Dawn 2N Missile Defense Radar, a pyramid built to track nuclear war. The Dawn 2N missile defense radar was one of the most visually striking and strategically significant military structures ever built by the Soviet Union. Rising from the outskirts of Moscow like a concrete pyramid, Dawn 2N was designed to serve as the central sensor of the Soviet capital's anti-ballistic missile defense system. Its purpose was stark and uncompromising: detect, track, and guide interceptors against incoming nuclear warheads during a full-scale missile attack. Development of the Dawn 2N began in the late 1960s as part of the A-35 and later A-135 missile defense programs. Soviet leadership viewed the protection of Moscow as a political and strategic necessity. While arms control treaties limited nationwide missile defense systems, the Soviet Union focused its efforts on creating a highly concentrated defensive shield around its capital, with Dawn 2N at the core. Construction took years and required extraordinary resources. The radar structure stands roughly 33 meters tall, with 4 massive, sloped faces arranged in a truncated pyramid shape. Each face houses a large phased-array radar antenna, allowing Dawn 2N to scan the sky in all directions without physically rotating. This configuration gave the system the ability to track hundreds of targets simultaneously at ranges extending thousands of kilometers. Technologically, Dawn 2N was far ahead of most contemporaries. Its phased-array radars could distinguish between real warheads, decoys, and debris, a critical requirement in the era of multiple, independently targetable re-entry vehicles. The system was designed to operate under conditions of intense electronic warfare, nuclear detonations, and atmospheric disturbance, ensuring functionality even during the chaos of a nuclear exchange. The radar became operational during the late 1980s and was integrated with interceptor missiles armed with nuclear warheads, intended to destroy incoming missiles outside or near the atmosphere. This approach reflected Soviet acceptance that missile defense itself might involve nuclear detonations over defended territory, prioritizing survival over collateral damage. For NATO planners, Dawn 2N was deeply unsettling. It suggested that the Soviet Union was pursuing a form of strategic insulation, potentially undermining the logic of mutual vulnerability that underpinned nuclear deterrence. Even if the system could not stop a full-scale attack, it raised the possibility that limited strikes or coercive threats might be blunted. Dawn 2N also carried immense symbolic weight. Its monumental form, permanent emplacement, and secrecy conveyed confidence and resolve. Western intelligence agencies devoted significant effort to understanding its true capabilities, often assuming worst-case performance due to limited visibility into Soviet testing and operational doctrine. Dawn 2N remains operational today, upgraded and maintained by Russia as part of Moscow's missile defense network. It stands as a reminder that the Cold War contest was not only about weapons, but about systems designed to function at the very moment civilization itself might be under attack. As a pyramid built to track nuclear war, Dawn 2N embodied the Soviet belief that even an apocalypse could be engineered against. Mir Space Station. Permanent Soviet presence in orbit. The Mir space station was one of the most ambitious and enduring achievements of the Soviet Union, representing a decisive shift from short-term space missions to the concept of permanent human presence in orbit. At a time when space was viewed as the ultimate strategic high ground, Mir demonstrated that the USSR could not only reach orbit, but live and work there continuously for years. Development of Mir began in the late 1970s, building on experience gained from the earlier Salyut space stations. Soviet planners envisioned a modular orbital complex that could be expanded over time, repaired in space, and adapted for long-duration missions. This approach contrasted sharply with Western reliance on short shuttle flights and raised concerns that the Soviet Union was pursuing sustained military and intelligence capabilities in orbit. Mir was launched on the 19th of February, 1986, from the Baikonur Cosmodrome. The initial core module was followed by a series of additional modules added over the next decade, including Kvant-1, Kvant-2, Kristall, Spectre, and Priroda. Each module expanded the station's capabilities, providing laboratories for astrophysics, Earth observation, materials science, and life sciences. At its peak, Mir weighed over 130 metric tons, making it the largest artificial object in orbit at the time. One of Mir's most alarming aspects for Western observers was its longevity. The station remained continuously inhabited from 1989 to 1999. Setting records for human endurance in space. Cosmonauts conducted missions lasting 6 months to over a year, proving that extended habitation in microgravity was possible. This raised strategic questions about future military space stations, on-orbit command platforms, or surveillance systems that could operate indefinitely above Earth. Mir was also deeply intertwined with military infrastructure. Many experiments were dual-use, combining civilian science with potential reconnaissance, sensor testing, and communications research. Earth observation modules provided high-resolution data, while long-duration missions allowed the study of human performance under conditions relevant to space-based operations. The station faced numerous technical challenges, including power failures, fires, and a collision with a resupply spacecraft in 1997. Despite these incidents, Mir continued operating, reinforcing perceptions of Soviet engineering resilience and risk tolerance. Western analysts closely monitored each crisis, aware that the lessons learned could inform future orbital systems. After the collapse of the Soviet Union in 1991, Mir became a symbol of continuity amid political upheaval. Russia continued operating the station with international partners, including the United States, but its origins as a purely Soviet project were never forgotten. Mir was deorbited in 2001, ending 15 years of service. Its impact, however, extended far beyond its operational life. Mir demonstrated that permanent occupation of space was achievable and sustainable, reshaping global expectations of orbital presence. For the West, it was a constant reminder that the Soviet Union had not merely reached space, but claimed it as a long-term domain of strategic activity. Sari-Shagan Anti-Ballistic Missile Test Range, proving ground for nuclear defense. The Sari-Shagan Anti-Ballistic Missile Test Range was one of the most secretive and strategically sensitive military installations created by the Soviet Union. Built to test defenses against nuclear attack, it became the core location where Soviet missile interception concepts were transformed from theory into operational systems. Its existence alone signaled that Moscow was preparing not just to launch nuclear weapons, but to survive and fight through a nuclear exchange. Construction of Sari-Shagan began in 1956 on the remote shores of Lake Balkhash in Kazakhstan. The site was selected for its isolation, vast open space, and ability to support long-range missile trajectories without outside observation. From the beginning, it was intended to support experimental work on intercepting ballistic missiles, a task that required extreme precision, advanced sensors, and powerful computing systems far beyond conventional air defense. Over time, the test range expanded into a massive military scientific complex. It included missile launch pads, interceptor silos, command bunkers, telemetry stations, tracking radars, and impact zones stretching hundreds of kilometers. High-powered radar systems were installed to monitor missile launches, warhead separation, decoys, and interception attempts in real time. Entire residential settlements were constructed to house engineers, scientists, soldiers, and support personnel, making Sari-Shagan a self-contained city dedicated solely to nuclear defense research. The range played a central role in the development of Soviet anti-ballistic missile systems, including the A-35 and later A-135 missile defense networks protecting Moscow. Interceptor missiles tested at Sari-Shagan were often armed with nuclear warheads, reflecting Soviet acceptance that stopping incoming ICBMs might require detonations in the upper atmosphere or near space. These tests explored guidance accuracy, reaction time, and the ability to function under intense electronic interference. For NATO planners, Sari-Shagan was deeply unsettling. Even limited missile defense capability threatened to undermine the concept of mutual vulnerability that stabilized nuclear deterrence. If one side believed it could intercept part of a retaliatory strike, it might be tempted to take greater risks. This concern directly influenced arms control efforts, including the 1972 Anti-Ballistic Missile Treaty, which sought to limit nationwide missile defenses. Despite treaty restrictions, testing activity at Sari-Shagan continued under various research classifications. Western intelligence agencies struggled to determine the true effectiveness of Soviet missile defense efforts, forcing worst-case assumptions in strategic planning. The uncertainty surrounding the range amplified its psychological impact far beyond what was publicly visible. Sari-Shagan embodied the Soviet belief that nuclear war was not only about destruction, but also about control and survival. As a proving ground for missile defense, it challenged the foundations of Cold War deterrence and remains one of the most consequential military research sites ever constructed. Ural 4320, Military Industrial Expansion, Mass Production for Endless War Readiness. The Ural 4320 military industrial expansion was not a single factory or vehicle program, but a vast production ecosystem designed to ensure that the Soviet Union could sustain large-scale conventional and nuclear war under the harshest conditions. Centered on the Ural automotive plant in Mias, this expansion turned the Ural 4320 truck into one of the most widely produced and strategically important military vehicles of the Cold War. Development of the Ural 4320 began in the early 1970s as a successor to earlier Ural military trucks. Soviet planners required a standardized, highly reliable off-road vehicle capable of operating across snow, mud, desert, mountains, and frozen terrain with minimal maintenance. The result was a 6x6 all-wheel drive platform powered by a robust diesel engine, engineered for simplicity, durability, and mass production rather than technical sophistication. What made the Ural 4320 expansion a mega project was scale. Production facilities were enlarged to churn out tens of thousands of vehicles annually, supported by a nationwide supply chain of steel mills, engine plants, component factories, and rail logistics hubs. The Ural Mountains region was deliberately chosen for strategic depth, placing production far from potential Western strikes while maintaining access to raw materials and labor. Entire cities and worker settlements grew around the factories, forming a permanent war production backbone. The Ural 4320 was designed to be endlessly adaptable. The same chassis could serve as a troop carrier, fuel tanker, missile launcher support vehicle, communications platform, radar carrier, mobile workshop, or artillery tractor. This modularity allowed the Soviet military to standardize training, maintenance, and spare parts, while supporting a wide range of battlefield roles. In wartime planning, this meant damaged units could be rapidly replaced and reconfigured without disrupting operations. From a Western perspective, the industrial logic behind the Ural 4320 was deeply concerning. Unlike prestige systems built in limited numbers, this program emphasized quantity, resilience, and redundancy. Even if factories were damaged, production could be shifted or resumed quickly. Even if vehicles were lost in large numbers, replacements could flow continuously from the industrial heartland. The truck's off-road capability reinforced this threat. The Ural 4320 could operate far from paved roads, enabling large formations to maneuver through terrain NATO forces assumed would slow or channel Soviet advances. Its ability to function in extreme cold made it especially suited to Northern Europe and Arctic-adjacent theaters. The Ural 4320 remained in production for decades and continues to serve in various forms today, underscoring the longevity of the design. Its significance lay not in cutting-edge technology, but in the Soviet commitment to preparing for sustained industrial-scale conflict. The Ural 4320. Military-industrial expansion alarmed the West because it represented readiness without limits. It showed that the Soviet Union was not planning for a short war, but for a prolonged struggle in which logistics, replacement, and endurance would decide the outcome. Kola super-deep borehole, drilling deeper than any nation before. The Kola super-deep borehole was one of the most ambitious scientific and industrial projects ever undertaken by the Soviet Union, pushing the limits of engineering far beyond conventional resource extraction. Located on the Kola Peninsula near the Arctic Circle, the project aimed to drill deeper into the Earth's crust than any nation had ever achieved, reaching depths that transformed a scientific experiment into a symbol of Soviet technological audacity. Drilling began in 1970 under the direction of Soviet geological and scientific institutes. Officially, the project was framed as a purely scientific effort intended to study the structure and composition of the Earth's crust. However, its scale, secrecy, and location inevitably attracted the attention of Western intelligence agencies, who viewed it as a potential dual-use project linked to underground military research, seismic monitoring, or hardened infrastructure development. The borehole, designated SG-3, was not a single straight shaft but a complex system of branching holes drilled using specially designed equipment. Engineers faced extreme conditions as depth increased. Temperatures rose far beyond predictions, exceeding 180 degrees Celsius, placing enormous stress on drilling tools, electronics, and materials. Rock formations behaved unpredictably under pressure, forcing constant redesigns and technical improvisation. By 1989, the Kola super-deep borehole reached a depth of 12,262 meters, making it the deepest artificial point ever created on Earth. This achievement surpassed all previous drilling records and remains unmatched today. The depth alone required decades of continuous effort, custom-built drilling rigs, and a sustained flow of resources rarely committed to a single scientific project. The discoveries made during drilling challenged established geological assumptions. Scientists encountered unexpected rock formations, high levels of trapped gases, and evidence of water deep within the crust, contradicting prevailing models. These findings had implications not only for geology, but also for understanding seismic activity, heat transfer, and the behavior of the Earth under extreme conditions. For Western observers, the project raised strategic questions. The ability to drill to such depths suggested potential applications in underground command facilities, hardened missile silos, or deep Earth sensing systems capable of detecting nuclear tests. During a period when underground survivability was a core concern of nuclear strategy, the Soviet willingness to invest in extreme depth drilling was unsettling. The project slowed during the late 1980s as technical challenges mounted, and funding became increasingly strained. By the early 1990s, following the collapse of the Soviet Union, work was officially halted. The site was eventually abandoned, leaving behind sealed boreholes and decaying infrastructure. The Kola super-deep borehole demonstrated that Soviet ambition extended not only upward into space and outward across continents, but downward into the planet itself. By drilling deeper than any nation before, the project embodied a mindset that treated physical limits as obstacles to be challenged, reinforcing Western perceptions of a rival willing to pursue extreme solutions in pursuit of strategic and scientific advantage. Transpolar Strategic Bomber Network, Arctic air power at the edge of the world. The Transpolar Strategic Bomber Network was one of the most formidable and psychologically powerful components of Soviet Cold War military doctrine. By turning the Arctic from a natural barrier into a primary attack corridor, the Soviet Union reshaped the geography of nuclear warfare and forced the West to confront threats emerging from the most remote region on Earth. The concept gained momentum during the early 1950s, as long-range aviation and nuclear weapons matured simultaneously. Soviet strategists recognized a critical geographic reality. The shortest route between the USSR and North America ran directly over the North Pole. Traditional Atlantic and Pacific defenses offered limited protection against attacks coming from the Arctic, an area characterized by vast distances, extreme weather, and minimal infrastructure. This realization drove the creation of a transpolar bomber strategy built around reach, surprise, and persistence. At the center of the network were long-range bombers such as the Tu-95 Bear and later the Tu-160 Blackjack. The Tu-95, entering service during the mid-1950s, was specifically engineered for extreme endurance, high-altitude flight, and reliable operation in sub-zero conditions. It could carry nuclear weapons thousands of kilometers across ice-covered regions where interception was difficult and early warning was limited. The later Tu-160 expanded this capability with greater speed and payload, reinforcing the credibility of Arctic strike routes. Supporting these aircraft required massive infrastructure investment. The Soviet Union constructed and expanded remote Arctic and subarctic air bases across Siberia and the northern coastline. These bases featured reinforced runways, heated hangars, fuel depots, radar coverage, and housing for crews and support personnel. Many installations were deliberately placed far from major population centers, reducing vulnerability and complicating Western intelligence collection. Navigation and command in the Arctic posed unique challenges. Conventional magnetic compasses were unreliable near the pole, forcing reliance on celestial navigation systems, specialized polar charts, and later satellite guidance. A network of radar stations, communication relays, and command centers coordinated bomber movements across thousands of kilometers of hostile environment. For NATO, the transpolar bomber threat was deeply destabilizing. Existing air defense systems were poorly positioned to detect and intercept attacks over the Arctic. This vulnerability drove enormous Western investments, including the distant early warning line across North America, fleets of interceptor aircraft, and continuous radar surveillance. Even so, complete coverage of the Arctic proved impossible. Beyond its combat role, the network functioned as a tool of pressure. Regular patrols near Arctic airspace tested Western defenses, gathered intelligence, and demonstrated readiness. These flights kept the threat visible and constant. Although ballistic missiles eventually reduced the centrality of bombers, the transpolar strategic bomber network remained a critical pillar of deterrence. By weaponizing geography itself, the Soviet Union placed nuclear air power at the edge of the world, forcing the West to defend the planet's most unforgiving frontier.